You know, so much of our world is governed by things we can't actually see. Today, we're going to pull back the curtain and explore the hidden language of the universe. We're going to break down two really fundamental tools from vector calculus, divergence and curl, that help us visualize and measure the invisible forces that are shaping everything around us.
Right? I mean, you can't see a magnetic field, you can't see the flow of heat through a wall, but these forces are incredibly powerful. So how in the world do scientists and engineers actually get a grip on them? Well, it turns out the answer lies in some surprisingly elegant math.
So, here's the game plan. We'll kick things off with the basic idea of a vector field. Then, we'll dive into our two main tools for measuring it, divergence and curl. And finally, we'll see why this math is so incredibly important for understanding everything from the weather to the fundamental laws of physics.
Okay, first things first, we need to set the stage. And the stage where all this action happens is called a vector field. Just think of it as an invisible landscape of force.
So, what is a vector field, really? At its heart, it's just a space, could be this room, could be the whole planet, where every single point has a little arrow attached to it. And that arrow, that's a vector. It just tells us two things, a direction and a magnitude, or, how strong it is.
The absolute best way to picture this is a weather map. You've seen them, right? At every single point on that map, there's an arrow showing you which way the wind is blowing and how fast it's going. That entire map, that's a perfect example of a vector field. So let's just take that idea and apply it to other invisible forces. All right, now that we have a feel for vector fields, let's introduce our first tool, divergence. This one is all about measuring how much a field is spreading out from or flowing into a single point.
Yeah, so divergence basically measures the rate at which something, like air or maybe a fluid, is flowing out of a specific point. It's like asking the field a question. Hey, at this exact spot, are you acting like a source or are you acting like a drain? Divergence gives us a single number that just answers that question for us.
To make this really click, let's stick with the idea of water. Picture a sprinkler head out on a lawn. Right at that point, water is just appearing, right? And it's flowing outwards in all directions. This is the perfect picture of what we call a source.
So if we could measure the divergence right at that sprinkler head, we get a positive number. Positive divergence is just the math's way of saying, hey, you found a source. This is a point where the field is expanding outwards.
Okay, so what's the opposite? Well, think about a drain in a sink. Here, water isn't being created, it's flowing into a single point and, vanishing.
And right at that drain, the divergence is a negative number. That's all negative divergence means. It's pointing to a sink, a point where the field is contracting or flowing inwards.
So what if the divergence is 0? Well, that just means there are no sources and no sinks anywhere. This special kind of field has a cool name. It's called solenoidal. Think of water flowing smoothly in a pipe. No water is being added, none is being taken away. That's what we'd call an incompressible flow.
Okay, let's move on to our second tool. So if divergence is all about spread, our next tool, curl, is all about spin.
Curl gives us a way to measure the microscopic rotation inside a vector field. It's basically asking, if we could zoom in on any single point in this field, would the stuff flowing around it tend to swirl or rotate right there?
And here is a fantastic way to think about it. Imagine dropping a tiny, microscopic paddle wheel anywhere in this field. If the flow around it makes that little wheel spin on its axis, then yep, the field has curl at that point. If the wheel just gets pushed along without spinning at all, then there's no curl. Simple as that.
And just like with divergence, there's a special name for a field where the curl is 0 everywhere you look. We call it an irrotational field. Now this is key. Even if the overall flow seems to be moving in a big circle, if there's no tiny scale spinning happening, it's still irrotational.
So we've got spread, which we measure with divergence, and spin, measured by curl. Let's put them side by side for a second, just to see how they really stack up.
This really lays it all out, doesn't it? Divergence is measuring the outward spread, think sprinklers or drains, and when it's 0, the field is solenoidal. Curl measures that microscopic spin, think of our little paddle wheel, and when it's 0, the field is irrotational. They are two totally different questions you can ask about the exact same field.
And that's the key takeaway right there. A field can have both divergence and curl. It can have just one of them, or it can have neither. They are completely independent properties that describe different behaviors happening at every single point in that invisible landscape.
Okay, so this is all pretty cool in theory. But where does this stuff actually get used? Why does any of this math matter? Well, let's connect it to the real world.
The applications are just huge. I mean, these tools are the absolute bedrock of electromagnetism. They describe how electricity and magnetism work. They're essential for fluid dynamics, helping us design airplanes and predict the weather. Even engineers use them to understand the hidden stresses inside a bridge.
But to show you just how profound this is, let me give you one specific example from physics. It is one of the most elegant and important statements about how our entire universe is built. This right here, this is one of the famous Maxwell's equations, a true cornerstone of physics. And in the language we just learned, it says that the divergence of a magnetic field, that's the B, is always zero. That simple statement means the magnetic field is solenoidal. It has no sources and no sinks. And that is the mathematical proof that you can never, ever find an isolated north or south magnetic pole. They always come in pairs. It's a fundamental truth of our universe, described perfectly by the concept of divergence.
So, from a simple idea of spread and spin, we get a language that can describe the fundamental laws of nature. It just makes you wonder, right? As we keep exploring the universe with these mathematical tools, what other unseen truths are just waiting to be explained?